Voyager 1 is the most distant human-made object in history, and in 2012, something on the other side of our solar system started pushing back. Pause. Let that land. Scientists at NASA tracked the signal. They ran the numbers. They checked for instrument failure. They ruled out every known force in physics. And then, quietly, in a paper most people never read, they wrote 4 words that don't belong in a NASA document. We cannot explain this. Right now, in 2024, NASA's Interstellar Mapping and Acceleration Probe, IMAP, is in final preparation for launch. Its entire mission is built around one goal: understand what's happening at the edge of our solar system. Because Voyager went there. Voyager crossed the boundary. And what it sent back doesn't match a single model we built to predict it. Here's the question I want you to hold on to until the end of this video. If our best physics, the same physics that landed rovers on Mars and predicted gravitational waves, can't explain what Voyager found, what does that mean for everything we think we know about interstellar space? We'll come back to that. But first, you need to understand what Voyager was supposed to find, because the gap between that and what it actually found is where this story lives. Voyager 1 launched on September 5, 1977. It was never designed to leave the solar system. Its original mission was Jupiter and Saturn, a planetary flyby, nothing more. But something unexpected happened. The gravitational slingshots worked too well. Voyager gained so much speed that NASA realized this probe isn't coming back, ever. So they kept it going. For decades, Voyager traveled outward, past Jupiter, past Saturn, past Uranus and Neptune's orbit, past the Kuiper Belt. By 2004, it reached a region called the termination shock, where the solar wind, that constant stream of charged particles blasted out by the sun, begins to slow down. This was expected, predicted, modeled for years. Think of the solar wind as a bubble. The sun breathes it outward in all directions, a protective envelope that scientists call the heliosphere. Inside the heliosphere, our solar system, our planets, our everything. Outside it, interstellar space, the space between stars, a region filled with material ejected by ancient supernovae, by distant dying suns, stuff that has been drifting through the galaxy for billions of years. The boundary between these two regions is called the heliopause, and for 50 years, scientists had a detailed, confident model of what it looked like. They imagined it as a comet shape. The sun moves through the galaxy at about 84,000 kilometers per hour. So naturally, like a boat moving through water, the heliosphere should be blunt at the front and stretched into a long tail at the back, called the heliotail. Tidy, logical, elegant. In August 2012, Voyager 1 crossed the heliopause. It became the first human-made object to enter interstellar space, and that's when things stopped making sense. When Voyager 1 crossed the heliopause, the transition should have been gradual. The models predicted a slow handoff, solar wind fading, interstellar particles increasing, magnetic field direction shifting smoothly. That's not what happened. The magnetic field didn't shift direction at all. Scientists expected the field lines to change angle when Voyager left the sun's domain, because inside and outside the heliosphere, the magnetic environment should be fundamentally different. Instead, the field stayed almost parallel on both sides of the boundary. NASA physicist Leonard Berlanga, who has studied Voyager data for decades, described it in the journal Science as a major surprise. The boundary was sharp, abrupt, more like a wall than a transition zone. But that's not even the worst part. Here's where it gets genuinely strange. As Voyager crossed into interstellar space, scientists expected to see a surge of galactic, cosmic rays, high-energy particles from outside the solar system that the heliosphere normally blocks. And they did see that surge. That part was correct. What wasn't correct was where the particles were coming from. Some of the energetic particles Voyager detected weren't streaming in from interstellar space. They were moving in directions that don't correspond to any known source, not the sun, not known nearby stars, not the galactic plane. Researchers at the Johns Hopkins Applied Physics Laboratory flagged this in 2013. The particles were arriving from directions that, statistically, shouldn't be producing them. In 2019, a follow-up analysis using Voyager 2's crossing, which happened in November 2018, 6 years after Voyager 1, confirmed it. Both probes entering interstellar space at completely different locations detected similar anomalies, same weird particle behavior, same boundary strangeness. Two data points separated by billions of kilometers telling the same inexplicable story. And here's what nobody talks about outside of specialized journals. Remember that comet-shaped model? The blunt front, the long stretched tail? In 2015, researchers analyzing data from NASA's IBEX mission, the Interstellar Boundary Explorer, published a paper in Nature Astronomy proposing something radical. The heliosphere isn't comet-shaped at all. It's round, spherical, like a croissant or a crescent, with no extended tail. Then in 2020, a separate team using a completely different methodology confirmed the same thing. The heliotail that astronomers assumed existed for half a century, that every textbook diagram shows, may not exist at all. Which means every simulation, every model, every prediction about what Voyager would encounter was built on a shape that was wrong. And if the shape is wrong, the behavior of everything inside it, the particle flows, the magnetic fields, the boundary interactions, needs to be recalculated from the ground up. Voyager is out there right now, still transmitting 24 billion kilometers away, powered by a nuclear battery producing less electricity than a dim light bulb. And every signal it sends back adds to a picture of interstellar space that our best physics was not built to explain. Here's why this matters beyond scientific curiosity. The heliosphere is Earth's first line of defense against the galaxy. It deflects a significant portion of galactic cosmic rays, high-energy radiation that at sufficient doses damages DNA and increases cancer risk. Without it, Earth's surface radiation environment would be measurably different. We've always assumed this protection was stable, constant, that the heliosphere has been roughly the same shape and strength for millions of years. But the sun moves through different regions of the galaxy, and those regions have different densities of interstellar material. Some researchers, including a team from the Harvard-Smithsonian Center for Astrophysics, have proposed that Earth may have passed through periods where the heliosphere was compressed, possibly even penetrated, exposing the inner solar system to elevated cosmic ray bombardment. There is a hypothesis, still debated, still unproven, that these periods correlate with mass extinction events in Earth's geological record. We cannot confirm that yet. The data isn't there. But here's the thing. The data isn't there because we've only sent one probe through the heliopause. One. In the entire history of human spaceflight. Voyager 1 is operating on instruments designed in the 1970s, instruments that weren't built to answer the questions it's now raising. It can't measure everything. Whole categories of phenomena happening at the boundary right now are invisible to it. And every crude deep space mission we're planning, Artemis, Gateway, the long-term Mars architectures, will require humans to spend extended time outside the protective layers of Earth's magnetic field, in regions increasingly exposed to the interstellar environment we don't understand. We are designing life support systems, radiation shielding, mission durations, all of it, using models that Voyager's own data suggests are incomplete. Not wrong in a small way, wrong in a structural way, wrong about the shape of the thing. So, the question I planted at the start: if our best physics can't explain what Voyager found, what does that mean for everything we think we know? It means we're at the edge of something, not just physically, the edge of the solar system, but intellectually. The edge of a model that has served us well and is now showing cracks in the places we can't easily reach to fix. IMAP launches soon. It will map the boundary in higher resolution than anything before it. It may answer some of this. It will almost certainly raise new questions. Voyager is still out there, still transmitting, still, after 47 years, teaching us things we didn't expect to learn. If this changed how you think about what's beyond our solar system, subscribe. Because next week, we're going somewhere even harder to explain.